Welcome to the CFE Media and Technology Education Session, Back to Basics, Control Systems, Drives, and Motors. I'm your moderator, Amara Rausgis with CFE Media and Technology. Let's get some important things out of the way before we dive into this topic. In keeping with RCEP policy, please take some time to read the quality assurance slide. This session is designed for technicians and engineers who want to understand the fundamentals and some best practices of control systems, drives, and motors. If you're interested in earning one AIA CES approved learning unit for this event, you need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the resources option on the left side of your screen. In keeping with the American Institute of Architects Continuing Education System Policy, please take some time to read the quality assurance slide. Thank you. For a seamless online experience, here are some tips. The question and answer session with Richard Vedvick will start in approximately 45 minutes at 2:45 Central, 3:45 Eastern, or immediately after this presentation ends. Answers will be archived with the session. You can see the Q&A details in the Meetings tab on the left side of your screen. Zoom invite details can be found in the Additional Resources tab under the Q&A session. Additional resources can be viewed and downloaded on the left side of your screen below the session's agenda. If you'd like to take notes during the session, click on the left panel labeled Notes to do so. The session is available on demand if you need to come back at any time. Here's a list of the learning objectives. We'll touch on these in today's presentation. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. There are also underlined hyperlinks to references and resources throughout the presentation. Now let's meet our expert presenter, Richard Vedvick. Richard Vedvick has experience in the healthcare, education, commercial, and government sectors. His electrical engineering experience includes lighting design, power distribution, emergency power systems, and fire alarm systems. For acoustical services, Rich collaborates with the design team for optimal architecture acoustical finishes, voice notification systems, and mechanical noise mitigation. He's a member of the Consulting Specifying Engineer Editorial Advisory Board and was a 2015 Consulting Specifying Engineer 40 Under 40 Award winner. All right, Rich, let's get started.
Thanks, Amara. Now you may wonder, why is an electrical engineer talking about all this mechanical stuff? Well, as a project manager, I do spend a lot of time in front of my clients speaking on behalf of the mechanical team. And what I found is, as an electrical engineer, I have a unique perspective of how all these things work, and I do need to have a basic understanding so that way I can communicate effectively to the facility, to architects, and to owners. And we're going to start with controls. And by controls, what we typically talk about is a building automation system or a building management system. Now, the point of all of this is to take the individual points and sensors that allow mechanical equipment, mechanical systems, and a variety of other pieces of equipment and systems to properly function and to enunciate. The designer needs to understand the requirements and expectations that the owner has. And what do we mean by that? Well, they're going to have operational requirements and that essentially affect whether or not the system is going to perform at different points in time during the day, whether it's going to change, whether it's going to evolve or stay consistent. We need to understand reliability and redundancy as well. Now, a network is what's going to allow all of these systems to interact with each other. And we have a couple graphics on the screen. On the top, we have what we would consider to be the fundamentals of a large system, where we actually have a local area network that connects to a server, cloud servers, and a workstation computer to allow users at multiple points throughout the campus or remotely to view all the aspects of the system. On the bottom, we have a smaller example. This might be more common in a smaller building where we don't necessarily need remote access. Now, in this case, the actual interface or the brains of the operation in the system are going to be the points of programming. So you're going to ask your client, Where do you want access to this information? And what do you want it to look like? Another question you're going to have is how much data would you like to access? We call that trends or trending. If I want to access trends over the last 24 hours or last 2 weeks, I need to understand how many points and how much information I have to store. Now, it's really important that engineers take this into consideration at the very beginning because it's going to affect the type of system that you're going to want to use. Now, there's a variety of ways that these building automation systems can communicate. BACnet is my personal favorite because I don't have to worry about the individual points. I can actually just say connect to the system via BACnet, and then all the information that the vendor provides is available for use. Now, another common system that we run into is Modbus. And Modbus is a similar version. It can sometimes take the place of BACnet in very small systems. But it's a digital communication protocol where you use a twisted shielded pair, and I can gain a variety of points and access. Electrically, we use Modbus commonly for like generators and transfer switches, paralleling gear and the like, where we want to communicate more than just a single point. It can be more cost effective, for example, than running individual wires to get 12 individual points. I can just run a twisted shielded pair and have BACnet or Modbus. Now, some of the other systems listed here might be archaic, like LawnWorks or ArcNet, and others are really just communication protocols. This is a general list for you to use as a summary, and then of course, if you're curious about the definitions of any one of them, you're welcome to look that up. Shown here is an example of the old versus the new. On the left, we have what's called a pneumatic system. Now, this is specifically for an air handling unit, and these pneumatic points were controlling dampers and air handling unit shutdown. Now, we had to move this thing. So are we going to really reuse a 30 or 40-year-old pneumatic system? And the answer is no. We're going to actually migrate all those points to digital because we already had a modern building automation system. But as you'll run into with a lot of remodels, you'll have a mix of old and new. The photo on the right is what we get to. That is an example of a modern digital building automation system cabinet. I can obviously fit a lot more cable, a lot more wires in there, and therefore have a lot more points in a much more compact package. So a building automation system needs inputs, right? Like Johnny 5, it needs input. So we're going to look at sensors, and sensors are going to give us all the variety of parameters that are available to us. Now, they can be hardwired, or they can be communicated over a digital means. So shown here on the right is an example of a control diagram. And here we have inputs and outputs, and we have sensors. So as shown here, we might be interested in air temp for a fan. We might be interested in humidity with how we're going to control our humidifier itself. We can even look at current, so we get status on whether or not a motor is running. We could do switches for whether or not we have an end stop. All of these are what the system is going to use to start performing calculations or start relaying the information on how the system's actually behaving. Now, points are a digital representation of what's actually happening in the system. I can have real points or virtual points. And a real point is going to be hardwired. It's important that engineers understand and define this very early on because it's going to affect the cost of the system. Hardwired points have cabling. They have to wire that cable. They have to be secured. And what if that point is 1,000 feet away? Obviously, there's a cost to that. And engineers have to consider what points they physically need. And then we have virtual points. And those are calculated based on some of the inputs that we get. For example, if I want to know dew point, I'm going to take the dry bulb temperature, which I can measure, and the relative humidity, which I can measure, and I'm going to calculate the dew point. That'd be an example of virtual. An analog input is going to vary. It means that we can actually get a position or a temperature that's going to vary. And technically speaking, it's usually resistance or voltage or current. I can also have an analog output that I can modulate. So if I want to say a damper is 30% or 40% or 60%, I can change that. But that's not an on or an off. That is simply, I'm going to say I want it at a certain percentage. So 0 to 100%, that'd be an example of an analog type or modulating control. Obviously, I also have digital sensors. Now, by digital, we don't necessarily have to be regulated to the binary ones and zeros that you'd see in a computer. We're really just saying it's a two-position state. It's on or it's off. It's good or it's bad, it's pass or it's fail. In a leak alarm, for example, it's a digital signal because we either have a leak or we don't have a leak. Relays, while they are considered somewhat of an analog component, they are a digital signal. It is a contact closure. Now, that's very common within our building automation system to use a variety of digital signals, a lot of digital inputs, a lot of digital outputs. On or off, yes or no. We're going to communicate with external systems with relays. But in addition, we can control solenoid valves. A solenoid valve is not partially open or partially closed, it's open or closed. We can also say start and stop. Start the motor and stop the motor. Now, if we want to control the speed of the motor, that's obviously going to be a variable type of control as opposed to a simple on or a simple off. It's very common for us to use the building automation system to perform other functions. I'm really interested, for example, from a lighting standpoint, to give the facility the ability to control lighting sequences or turn lighting on or off or control programming of lighting through the building automation system. You can also gain status of other systems that aren't mechanical. If you would like your technicians to get a text message every time the generator starts, building automation system is probably going to be your best way to do that. So we're going to have to coordinate, though, during design between all the various engineers, electrical, technology, et cetera, and the mechanical engineers of how many points do we need, because we're going to have to gather that data and call that out on the diagrams. Here's another example of a control diagram where we're actually defining DI as a digital input, DO as a digital output, AI as an analog input. So we have sensors and we have inputs. Now the VFDs that we're showing at the top here, those might be specified by the electrical, they might be specified by the mechanical. Regardless, that requires coordination. What do we actually want to know about those VFDs? What do we want to know about any of these other components? What if we want to start and stop this based on a fire alarm input, for example? Well, that's a contact closure. It gets back to our digital input. Engineers have to coordinate all of this to ensure that the design of the project is all-encompassing. We can't rely on the contractor or the manufacturer to figure out all of these points. The engineers have to communicate and quantify all of them. Now, if you're curious of what any of those silly symbols look like or meant, the best way to do that is by looking at a symbol list. So every time I look at any sort of a diagram, I'm always going to start with my key. What are these things meaning? And if you're an experienced engineer, you're probably used to the way that you've shown them. And if you're really experienced, you'll know that everyone shows things slightly different. Everyone kind of has their own way of communicating. What's important is that you use these diagrams and you use this aspect of a design to help convey the exact locations of where points need to be. If we're going to measure temperature, for example, it matters where we measure them. So the flow diagram is going to help us and the control diagram is going to help us. But then lastly, you're going to have to get out in the field and actually just look at it for yourself. So controls are fun. You know, we can do a lot with building automation systems, but what are we actually controlling? In some cases, it's going to be motors. So we're going to talk about motors in a couple different ways. I'm going to do applications with fans. I'm going to jump back and talk about motor technology. And then I'm going to go back to application and I'm going to talk about pumps. So when we talk about fan types, there's two main kinds. We got axial and we have centrifugal. The main design component of an axial fan is that flow is in the same direction as the motor shaft. So basically, in a propeller style, I have propeller fans like you see in a condensing unit. You even have these in your house. These are the fans that you set on the floor that kind of rotate back and forth. They're very cheap. They can't handle any static pressure though. So one of the main challenges that I had with the condensing unit was trying to make it quiet because these fans can be kind of noisy. And if I want to enclose a condensing unit, I have to be very careful about the amount of static pressure that I'm going to impart on those fans. Because if I impart too much static pressure, they actually slow down, they don't get their efficiency, and therefore we don't get adequate cooling. Now, if I want another example of an axial fan, I could go to tube axial. Now, these are a lot more common. A tube axial fan kind of produces airflow the same way an airplane wing produces aerodynamic lift. Now, one of the key characteristics is that air is actually swirling as it leaves. So we might need something to straighten that flow out if we think we're going to change directions too terribly quick. Now, I see these a lot in returns. So if I have an air handling unit that I'm trying to squeeze inside of a space, and I can't fit those extra return section modules, what I could possibly do is take a tube axial fan, hang it from the structure, and now I have my return fan that I can control just the same way you control any other fan. So they provide a useful opportunity. Now, as noted, they're typically going to be drawing in air, which makes them good for not only returns, but also exhaust applications. The last type of axial fan we'll talk about is vane axial. Now, what's different about this is instead of having a propeller, like you would with a propeller fan and a tube axial, the vanes are actually running like the length of the motor shaft itself. Now, you'll know this by simply looking at it because the center hub of the motor is going to be like half the size of the opening. It takes up, half of it, as opposed to where a propeller takes up the tube axial and propeller fans, the propeller actually takes up most of the space. You just kind of see a small shaft in the center. Now, these are really handy because they're easier to make adjustments. You can change the blades, you can change the quantity of blades, you can change the blade shape. They're really good for high flow, and they're also good for high pressure applications. It's also the most efficient axial style because I have more control over the way that the blades are oriented, and my blade size is based on the length, not necessarily the surface area. They tend to be pretty good for high efficiency. A more useful style of fan is a centrifugal fan. Now, unlike the axial fan, in which air is moving parallel to the shaft, a centrifugal fan, air is actually moving perpendicular. So if we take a look at these drawings that I very artistically created, you can see that air is flowing into the screen, right? Into the screen, into the center hub, and then it's being turned so it's spreading out perpendicular or radially. Now, a centrifugal fan requires a casing. If you were to just set this fan out in the middle of nowhere, you'd produce some air movement, but it wouldn't be very useful, unlike a propeller fan, which you can just set a propeller fan and it's going to do something. It's going to move air. So the casing is very important. The shape of the casing is also going to affect the efficiency. Now, there's a couple different types here. We're going to touch on each one. Radial is going to be probably your least efficient. It's also going to be fairly noisy. It's going to be capable of high pressure, but for the most part, we're not going to see these very often in HVAC unless we're dealing with really, really high pressures. But because of the low efficiency, it's probably not the best selection. What most of you are going to be very familiar with are forward curved centrifugal fans. And why is that? Because they're what's most commonly used inside furnaces. When I had to replace the forward curved centrifugal motor in my furnace, it was only $65 and it maybe took a couple hours. Not that big of a deal. Now, they're very low cost. They're fairly lightweight. They can build all the blades out of a single sheet of metal. And that's kind of what they're known for, right? You have a bunch of small, tiny little blades, 20, 30, or 40, that are pushing air. Now, because they are inexpensive, they also tend to be fairly low pressure based. So we're going to see these in residential applications primarily. If there's a commercial application, it's going to be fairly light commercial. But our next selection, that's what we're going to use for commercial. The backward inclined centrifugal, the workhorse of the centrifugal fan. So what makes this excellent is that our fan blades are actually bent backwards. So we have about 80% efficiency, whereas opposed we were down in maybe the 50s or 60s with, say, radial. And the air leaves at very low velocity from the blades as a result, which means we can generate high pressure, but we also have very low noise. So if you think about what are we trying to do in HVAC, we want to generate high static pressure, and we want to do it as quiet as possible. The backward incline is a pretty good compromise. It's more expensive than your forward incline, but it's so much more useful that we're going to be able to use these for most applications. Now, if we want to step it up a notch, we're going to look at our next and final centrifugal fan selection. If I really want to get the most out of a centrifugal fan, I'm going to go airfoil backward curved. Now, why is that? Well, I'm just simply changing the blade design to be as good as I possibly can. Now we can hit efficiencies better than 80%. I also have the highest pressure and the highest volume of air that I could possibly move and the highest efficiency. It's great. Why wouldn't we use it all the time? Well, it also obviously comes with an increase in cost. So as engineers make selections, they have to understand do I want the best, or can I settle for something that costs a little bit less but still does a really good job? So each of these types are going to find applications in your projects, and it's just important to understand what each one of them is. Now, we got to get a little technical here. We're going to talk about fan laws. Now, fan laws are essentially the proportional relationships between speed, flow, pressure, and power. They always apply. So that means if I want to figure out if I change one parameter, what happens to the other ones, I go to the fan laws. Electrically, we would consider Ohm's law and like how power and current and voltage and resistance relate to each other. This is the mechanical analog of that. Now, the important takeaways here are this very expertly drawn graph where we can see that CFM or flow is proportional to fan speed. Pressure is related to the square of fan speed. And energy, power, or horsepower, for example, is related to the cube of fan speed. That's kind of the basics of what that looks like. Obviously, as you're doing all of your calculations, you're going to be utilizing that information to determine if I change this, what's going to happen. An example of how to use that is with your fan curves. So we use fan curves to make selections. You can see here we've shown the relationship of pressure to air volume associated with a couple different types that I had previously talked about. Now, if you specify systems, you know fan curves pretty well. You know that they can include a bunch of other lines to tell you, well, this is the operating points. This is where they behave at different static pressures, how much power if I put into a certain type of fan. They're basically generated by the manufacturer and used by the engineer to make selections. It's important to understand that the fan energy index is a rating system to encourage better fan selections. So engineers need to be aware that the FEI, or fan energy index, is going to be useful to them to make the most efficient selection as possible. And it's based on the scheduled design or the scheduled duty point associated with that fan. Now, horsepower and motor brake power, right? What do these mean? What's the difference between a brake horsepower and a motor horsepower? Well, the brake horsepower is essentially the operating power that's required for that fan at that point. So you pick your fan's point on your fan curve. All right, I need, say, 7 horsepower in order to do my work. Now I have to make a motor selection, and that's going to be your motor horsepower, or MHP. So if I need 7 horsepower to make the fan work, I could, of course, pick a 7.5 horse. That's a standard size. Or I could pick a 10. And this is where engineers have to weigh cost versus benefit. If I want to build in some future capacity, then maybe I'm going to want to kick that up a notch. And we're going to see an example of that in the next slide. System effects. This is what allows us to determine whether or not we're using our power effectively. So on the photo on the left, we see 2 hard 90s coming into a fan. Now, I can tell you personally, this is a noisy and a terrible arrangement, and you shouldn't do this. The image on the right is what you should be aiming for, is a nice smooth transition. And this matters because as you change your inlet and outlet conditions of your fan, or you change your duct, you generate system effects. These are problems, not necessarily problems, but they're restrictions from the ideal. So as we generate system effects, we're going to change where we live on that fan curve. I can tell you the image on the left, that fan was not able to generate enough airflow because of the system effects and the offset in the ducts to actually be able to meet balance requirements. Now, when we talk about air, we also care about air density. And air density is going to be affected by ambient temperature as well as altitude. So as we move up in temperature and move up in altitude, air becomes thinner. Simply put, engineers need to understand that the fans, as they're selected by the manufacturer and specified, and all their data was probably in a nice, comfortable lab. As you apply your fan, you're going to generate a difference in the environment. And that difference in the environment means you have to make adjustments. You can't just pick a fan that was sized in a lab and say, this is going to work great in my application. You have to make adjustments based on the actual environment and the system effects. So we've had fun talking about fans, which is an application of motors. Now we have to talk about motors. There's a couple different types of motors that we're going to discuss. We're going to talk about AC and we're going to talk about DC. Now, why would you use one versus another? Well, AC motors are pretty popular in low cost and large in capacity because we use AC voltage in buildings. We're going to distribute voltage in buildings, and it'd be great if we could just use it as is. And the sinusoidal waveform has some useful features that we've designed motors to work around. Now, I can also use DC motors, but they're going to add a level of complexity because I don't have DC readily available. I actually have to convert voltage in order to be DC. But we can get really good efficiency with DC motors. So sometimes that makes a lot of sense. Now, it makes sense to talk about electrically commutated motors first because it kind of helps you understand the principles of magnetic fields. So I got a really expertly drawn diagram of my hand in the lower left-hand corner. And essentially, this is just showing you that if you have an XYZ axis that you make with your fingers, you can predict the magnetic force that's going to occur if you run current through a wire that's placed in a magnetic field. What we have on the right there, imagine that the red and the blue are north and south poles of a magnet, and that's the rotor. That's the center part of the motor. And my stator windings around the outside can generate a magnetic field. Now, this is going to be a push, weight, pull effect. So I'm going to push the motor away, because if I take a north pole and a north pole and try to push them together, they're going to repel. If I do a north pole and a south pole of a motor, they're going to attract. Well, I can generate these magnetic fields. So that's what an ECM does, is I can have 3, 6, 8, 10, 12, as many of the external stator windings as I want, to basically think of a spinning top that you just keep pushing and tapping with your finger. You can get the motor started, and you can actually run at very high speeds. So it's important to understand that magnetic fields are going to be manipulated in a DC motor and generated through coils and windings, unlike an AC motor, which we're going to look at next. So I have a couple different types of AC motors. And we should talk about the definitions. What is a rotor? What's the rotating part of the motor? It's the inside portion. The stator is the stationary part. It's the outside portion. Now, you can have windings in the rotor, or you can have windings in the stator, or both. And which way you configure that kind of depends on the motor topology that you're working with. You can also have magnets. Now, a motor works technically by just simply changing or generating magnetic fields that causes a rotational energy, working off the basic concept that if I have like magnets, they repel, and if I have opposite magnets, then they attract. So by simply varying the magnetic field, I'm able to generate that rotational inertia and generate rotation. Now, the primary difference between an induction motor, or called asynchronous, and a synchronous is the construction and how they get started. An induction motor is essentially self-starting. If I apply voltage and therefore induce current into the motor, then I can actually generate a starting rotation. And that's great. I might need to help that. There's some starting types that you'll see. These can be three-phase or they can be single-phase. The main concept of an asynchronous or induction motor is that it never runs at synchronous speed. It's always going to have a little bit of slip, meaning it's always going to be slightly slower than what it could be in an ideal world. And that's actually a design requirement, because that slight bit of difference is what generates current within the rotor and therefore allows for that changing magnetic field. Synchronous AC motors are fascinating, and sometimes they're just called synchronous machines because we can also use these as generators. Their primary claim to fame is that they run at synchronous speed. So they are very, very constant. They're fantastic in high accuracy flow applications or high accuracy rotational applications. Historically, they're also used in like clocks and timing circuits. The only way to change the speed, of course, is to use a VFD. I have to vary the frequency in order to change the speed of a synchronous motor. In addition, you can either do magnets on the inside or you can do DC wound coils. And the DC wound coils look kind of similar to what I showed you before with ECM, where we're running DC current and we're generating a magnetic field. Now, when it comes to brushed or brushless motors, there's a variety of benefits. Now, of course, if you read these next couple slides, you'll say, man, I should just use brushless for everything. But of course, there's a size limitation of electrically commutated motors. The benefit, of course, is that you get really, really high speeds. So a lot of the power tools you may have at your home might move to brushless. And that's been a pretty popular thing to do in the industry because I can get high speed. I get a lot of benefits. The carbon brushes themselves will eventually wear out. They generate noise, they have friction and heat, and therefore speed limitations. While it's not intended to be an exhaustive list, this is really a continuation. I would have fit it all on one slide, but of course I wanted you to be able to read the text. The takeaway is that brushless motors are fantastic for applications in which they can be used. They can be very accurate in positioning. They can be very good at speed and very high torque. But of course, they also come with a decent amount of cost and complexity. An ECM, for example, has the electronics built into the motor. That means I'm not just replacing the motor for a couple $100. I might be replacing it for $1,000. So you do have to communicate that with your client and say, I want to use ECMs for this application, but just know that when you have to replace it, it's going to be a lot more expensive than you're used to. The benefit is that I get really good speed control, and the speed control is actually inherent and built in. Now, of course, we care about efficiency. And there's been relationships to efficiency in a variety of classifications. We have NEMA, we have IE3. So we have premium, high, and standard. Essentially, efficiency is a measurement of, I put a certain amount in of work, right? And I only got a certain amount out. What happened to the rest of that stuff? Where does all that power go? Well, typically, it's going to go in the form of heat. We have losses. If we have a motor, we have wire. And if we have wire, we have resistance. So we just simply dissipate power in the form of heat in wire. And that happens on a regular basis. But inside of a motor, for example, we got the stator windings and we might have the rotor windings. And they're physically made of copper or some conductive material. And as I run current through them, I'm going to just have some loss and I'm going to generate heat. In addition, I also have general power losses and friction losses within the motor itself. And engineers should understand that sometimes a smaller motor is going to be more efficient in some aspects and less efficient in others. From a power factor standpoint, it's a pretty old idea. Obviously, it's been around for a long time. We understand that there's real power and imaginary power, and that we call that reactive or kVAR. And the main understanding that engineers should have is that if you have a very lagging power factor, for example, you're going to have a lot more reactive power that's essentially not doing any work. And utilities can commonly charge higher rates if you have a very substantially lagging power factor. Now, you can correct that with a variety of ways. I didn't mention this, but synchronous motors actually have the benefit of having a near unity or maybe even a leading power factor. So if you have a plant with a bunch of induction motors that typically are lagging, you could actually have synchronous motors for some applications, configure them to be leading and get power factor correction just inherent in the motor selections that you made. Now, for every piece of component, we need some sort of a disconnect. We have some electrical interface to motors or pumps or things like that. What you should know is that there's an SCCR, short circuit current rating, and that is how many amps, typically in the thousands, that component can handle before it fails. Now, you might say, well, I don't need 10,000 amps to run that equipment. I just need 10. Well, that's actually not where the SCCR rating is derived from. You see, the electrical engineer has to design the entire distribution system, and the transformers and the utility can supply a certain amount of current in the event of a fault. Say your motor winding short out. How much current is going to be drawn during that dead short? Well, the electrical engineer is going to determine that through a power system study. And what if they say, well, if you short that motor out, then 25,000 amps of current is going to be available for a few tenths of a second. Is that a problem? Is your disconnect going to explode? Well, that's where your SCCR rating comes in. So we're going to use SCCR and coordinate that. And mechanical and electrical engineers need to talk. Mechanical needs to ask, hey, what's the available fault current? What should I rate these disconnects at? And know that most standard non-fused disconnects are around 10,000. So if your engineer says, I got 25 or 35,000 amps, then you're going to have to move very likely to a fused disconnect. And you need to specify that and understand that early on. So not only do you comply, but you also don't put anyone in danger. As an electrical, I listen to my mechanical engineers say, well, we're going to have to sheave that motor in order to meet our balancing. I'm like, sheave a motor? What is that? I just kind of envision that you're shoving stuff inside of a motor to change the speed, but it's not. Sheaves are pulleys and pulleys are sheaves. And if you're mechanical, you probably know this already. And if you're not mechanical, maybe you thought sheaves were something different or something you did. Well, the term sheave a motor is really a misnomer, right? They should say, we're going to change the operational diameter of a pulley by simply changing the gap between the inside and outside rings of that pulley. So an adjustable sheave or an adjustable pulley is typically placed on the motor. And here's the concept. I have a motor with a pulley that spins a belt that then spins a fan, for example. Now the pulley on the motor is going to be fixed in size, and we can make the pulley on the fan adjustable. Why would we do that? Well, if we want to change the speed of that fan for balancing, for example, then we can do that by simply changing the operational diameter. We can pull it apart and allow the belt to sit more in the groove, or we can push it together and make the belt sit more on the top side. So we can change the operational diameter of that pulley. And we can change motor speed by using VFDs or other methods, but those are expensive. If I have an exhaust fan, for example, I might want to just be able to have a fixed flow, but then I have to balance it. So engineers can consider that an adjustable sheave or an adjustable pulley will give them some tunability when it comes time to actually balancing. It's also fun to note that there's a variety of belt types that could actually help you improve energy efficiency. We're all very used to V-belts, right? The typical style of belt that moves around two pulleys. The problem is that it doesn't really like to bend, so that's kind of inefficient, and it tends to slip anytime you have high torque. A cogged or a notched belt has the ability to replace a V-belt, and it just simply has better efficiency overall. It can bend much easier. If you want the maximum efficiency, though, you're going to be looking at a synchronous belt. This is basically a cogged belt or a notched belt with a matching pulley, so it doesn't have any slip, excellent high torque, and it's great in very wet and oily environments. Now, there's a wide variety of pump types, and quite honestly, you could have an entire class on each one of these and how to select them. So we're not going to spend a lot of time on them, but I do want to talk about some of the things that we want to coordinate with when it comes with pumps. Primarily, we're going to be looking at pump selection based on the type of fluid that we want to move, the flow, and the head pressure that we want to generate. And additionally, we're going to talk about the environment. In the case of a horizontal case that's split, this is a serviceable motor. We can take it apart physically. That's part of the design. But that means we have to have adequate space around that to work. Now, what you'll see in this photo is we have walking space. We can actually get to this pump, but one of the things you don't see is a disconnect or a VFD. Like, clearly, we have to control this, and I can tell you personally, I put a VFD on this motor. But where is it? Well, it can't be anywhere near this pump because it has serviceable components. And mechanical engineers need to tell their electrical engineer counterparts where they can and can't put their components. Now here we're going to see, look, I got VFDs along the back wall. But again, the mechanical engineer needs to tell the electrical, where can I physically put these? Now, end suction pumps are very common, right? I see them a lot of times in cooling tower applications. And they're great for chilled water. They can handle very large pump sizes and very large pipe sizes as well. 10, 12, 14, 16 inches is very common. But engineers have to communicate. If I'm going to do vibration isolation, we can see we have vibration isolation in the piping itself. It's that braided section right above the pump. And I also have something on the base as well. All of that takes up physical space, and it affects the serviceability. So we want engineers to think about these things, and we want them to coordinate. A vertical inline is great because I can fit it in all kinds of compact spaces, but then somebody has to get to it again. And they can be fairly heavy. If you're going to specify vertical inline pumps, make sure that somebody has a plan for how they're physically going to get to it. If they're smaller and somebody can hold it with one hand on a ladder, then that's probably fine. But if they're going to be larger, keep in mind that if you put a 50-pound pump, 10, 15 feet in the air and surrounded by pipes, you're going to give someone a hard time when they go to service it or replace it in the future. And as you're looking at all the various types, whether it's vertical turbine or piston or plunger, each one has a very specific application for which it's designed. We're not going to spend a lot of time on the Department of Energy Pump Energy Index, but it's important to understand that it affects a variety of pipes. So I have 3 slides here that we're going to go through fairly quickly. Understand that it was developed in 2016, and it took place essentially in 2020, January 1st. It affects a variety of pump types, and it also has a variety of system parameters. So whether or not your pump is required to meet this requirement is going to be based on the type of pump that it is and the actual operational parameters of that pump. And luckily, it doesn't include every pump. There's a variety of pumps that don't have to comply, and one of them being fire pumps, like the fire pump we see shown here. Now, if I want to start a motor, I talked before about like digital on-off controls with building automation systems. I can do what's called a contactor or an across-the-line start. That's where I simply say go, and I give a pump or I give a motor all the energy all at once. Well, we're going to have a lot of inrush associated with that, which can be problematic. Now, there's a variety of ways that I can generally start that motor. I can use a couple different what we call soft starters to maybe ramp up the voltage or kind of push the motor very gently and to get it going. Now, which one you're going to use is really going to depend on the electrical parameters and what that electrical system can handle. But a common way to do that is with VFDs. So variable torque, constant torque, that's a question that a lot of engineers have is which one am I using? So conveyors, for example, they're an example of a constant torque. That means my torque is high when I'm starting and it's maintained throughout the operational range. A variable torque motor is going to have torque that's fairly low and then it's going to get high as I get going in speed. So from a pump standpoint, a centrifugal pump is going to be variable torque, whereas positive displacement is going to be constant. Go back to our fan discussion. An centrifugal might be variable, whereas a reciprocating compressor might be constant. We have a variety of options as well, whether or not we want contactors, and the contactors, 2 or 3, is how do I want to isolate that VFD? And do I want to isolate the feed coming in and leaving simultaneously? A 3-contactor bypass is the easiest way to isolate that VFD. If I'm going to be operating a VFD and I'm going to have that be remotely located from my motor, because say my motor's on the roof and I have to have a disconnect at the roof, I have to interlock the two. I have to interlock, meaning if that disconnect on the roof is opened, the VFD, which might be inside the building for environmental reasons, knows that that contact's been opened. And it has to know. So engineers have to specify interlock disconnects and communicate that with the mechanical engineer, or if the electrical engineer is specifying the VFD, in order to make sure that those two work together. Now, anytime I use a VFD, I'm going to make sure I put it in the right spot. I tend to not put these things outside. They can get hot, they can generate heat, and more importantly, they're very sensitive electronics. So we want to be fairly careful about their application and ensure that when I place a VFD in a location, it's not going to fail prematurely simply because it's too hot. Now, many VFDs have a lockout range, in which case you can say if I have a problem frequency, that I can actually stop that frequency from being generated throughout its range. Maybe it skips 57 hertz. And that might be because 57 hertz generates a really problematic vibration. Now, we prevent bearing damage in motors whenever we use a VFD through what's called shaft grounding. It's important to note that the concept of a VFD is it has a high frequency switching, and that high frequency switching can generate a lot of higher voltages. It can also cause arcing. So if we don't have individual shaft grounding, it's separate from the motor itself. If we don't add that, then we can actually arc across the bearings. And if you have bearings that fail quickly or become noisy fairly quickly, that's probably a result of the arcing that's occurring. Now, luckily, it's pretty easy to either specify shaft grounding or even add it after the fact. And you can do inverter rated motors and inverter duty motors. And they basically have beefed up windings to handle those voltage spikes so they don't break down prematurely. But just because you have an inverter rated motor doesn't mean necessarily that you have grounding. So I say they do offer protection. I should actually say they do not offer protection. So that is something that you're going to want to coordinate with your motor specifier. And when it comes to insulation class, here we're talking about heat. Now, heat is going to be generated anytime you run current through a wire. Remember, that's part of our losses. So if I have a VFD, remember, I'm also causing spikes in voltages. I'm going to be generating a little bit more heat than I would if I didn't. So typically, when we look at classes, we're going to go with an F or an H if we're going to be running a VFD. We're also going to consider service factor. So if I have a higher service factor, then I'm allowing for a hotter hot spot. And what that means is that just because we have temperature heat that's being generated by current doesn't mean it's the same everywhere. We expect that at certain parts of the motor, it's actually going to be a little bit hotter than in other spots. So as we look at our hotspot allowances and based on our classes, we can increase that with our service factor. So really the takeaway here is that you're always going to take your environment into consideration for heat, for temperature, humidity, whether it's fans, whether it's motors, whether it's pumps, whether it's VFDs, We're always going to take our environment into consideration so that engineers are looking at projects holistically.
That was great. Thank you to Richard Vedvick for all that excellent information and a great presentation. Questions will be answered in a live Q&A on October 9th at 2:45 p.m. Central, 3:45 p.m. Eastern. Participate in the live Q&A with your Zoom invite details. These details can also be found in the Additional Resources tab on the left side of your screen.